This is our third bundle of applications, and in this bundle we will look at resistors and capacitors. Well, it's clear what the application is. Most circuits have R's and C's in them, and this is critical for all our circuit analysis. We're just missing inductors, which we study in the next half of 261 when we look at magnetic fields, and of course we don't look at active devices. In the capacitor examples, we will consider two conducting surfaces separated by a dielectric in three geometries: a parallel plate capacitor, a cylindrical capacitor, and a spherical capacitor. Our first example is to compute the resistance of a block of material with conductivity sigma. And you can see that the block of material has length L and cross-sectional area A. To compute the resistance, we just compute the potential difference across the faces, V21, divided by the current. This is a straight application of two of our integrals. The first is the potential integral, the work done against the field. That's the numerator right here. And the denominator, which we just recently studied, here is our friend J, vector J. Let's put the vector sign on it, sigma E dotted with ds. We did an application in class to compute the current, so we just have to compute this for the rectangular box under the assumption that the field here is uniform. You can see that it's pointing in the negative z direction, and it's uniform, so E0 is a constant. We just substitute into the formula for the potential, take the dot product, integrate against the field, going from Z1 to Z2, which is a distance L in the figure, and this is a simple integral to do. It's the integral of a constant from Z1 to Z2. E0 times L, and you could easily solve for V21 and E0 and L and get the relationship for E0. This is not a difficult thing to do. We do the same for the current. This is similar to the wire example we did in class. And so we have the current density in the direction of E. And so we're looking at like the current through the wire like we did in class, where everything is lined up here. And we just compute this. E is equal to E0 times minus AZ. The ds is also pointing in the negative direction. In this way here, there's our ds. Take the dot product, a bunch of constants again, and then multiplied by the area. So we get V1 sigma, V21 over L, which is our E value, times sigma times the cross-sectional area, just integrating a bunch of constants. So now we just substitute in here V21 over I, and the V21s cancel, and we get this final relationship that the resistance is equal to L over sigma A. The interpretation is that the resistance is proportional to the length of the resistor and inversely proportional to the conductivity and the area. A big area means a low resistance. A big conductivity means a low resistance. So that's really all there is to it. This also holds if the field, electric field, is uniform and the cross-sectional area of the conductor is something strange like an ellipse. Welcome to the first three capacitor examples in three geometries. The first is a parallel plate capacitor, and we've seen all this before. We've done all the calculations. This is an encapsulation of those calculations. We are going to assume that we can use the infinite sheet approximation, which means that the distance between the plates is much, much smaller than either the length of the plate L or the width of the plate W, so that everything is governed really by the area of the plate, in this case length times width. Capacitance calculation is straightforward. We do work against the electric field, so going from where the plate normally is grounded up to the charge plate, the positively charged plate. And to do the calculation, we just have to compute that work against the field given by this line integral. The line integrals are always straight lines in all these examples. They're very straightforward to do. And of course, the charge is equal to d, the vector d, which is epsilon E dot ds. Notice that this is not a closed surface. This is an open surface. So it's just adding up the charges on one surface. And we know that the vector d is coulombs per meter squared, multiplying in a dot product sense with the area element ds right here, and we get coulombs, which is charge. In most cases, since we assume that the charge is uniformly distributed, we don't have to actually perform an integral. We just multiply the charge times the surface area of the conducting plate or conducting surface. And we will use this not only in the parallel plate case, but the cylindrical case and the spherical case. The challenge is always to compute the electric field. Well, here are the details of the calculation, most of which we've seen before. We know that the field between a positively charged and negatively charged plate has a magnitude of sigma over epsilon naught. In this case, the field is pointing downward in the negative z direction, so we see the minus sign here, and the direction is az. Now we do the integral. We do work against the field going from here up to here, from the ground to the positively charged plate. Don't forget we have our famous friend the minus sign working against the field, going from z is equal to 0 to z is equal to d, and then the dot product of E. Here's E, this term here. Our line element is just in the z direction. Taking the dot product az dotted with az is equal to 1, then we have the integral from z is equal to 0 to z is equal to d of a constant, and so that integral is simply this. And the Q, the charge, is just the charge density times the area of the plate. And if we substitute in, we see that the sigmas cancel, and we're left with this classic result, epsilon naught A over D. This again is in the assumption that the separation distance between the plates is much smaller than the area of the plate in terms of the dimensions of the area, length times width, so we can use the infinite plane approximation for the electric field. Notice the units. The capacitance will always be the permittivity times the length to give us farads. The units of the permittivity are farads per meter, and then the other term is a geometry term. In this case, it's A over D, area over distance, has units of just distance, and so everything works out unit-wise. We get the standard formula that you've probably seen in many other physics courses. Here's the second example, a cylindrical capacitor. We've also seen most of this in class before. We have a central conductor of radius r1, and there's a uniform surface charge plus sigma on that central conductor. We have an outer conductor. It will be grounded. We will also assume that the length of this capacitor is much, much larger than the distance between these two conductors here, that distance. And so we can also use the infinite cylinder approximation to the field, neglecting the edges. So what do? Well, we have to compute Q over V, the charge on the positive inner cylinder, divided by the potential difference. So here are the general steps. Compute the electric field, line integrate it to get the potential, compute the charge, a simple multiplication of sigma times the surface area on which it is deposited, take the ratio to get the capacitance. All right, we start with calculating the electric field. This is the hardest piece. To do that, we use Gauss's law. So we surround the charge on the inner conducting cylinder by a Gaussian surface here. There's my Gaussian surface. I'll draw it like so you can imagine through the cylinder. It's another concentric cylinder. So there it is. Okay, you can imagine this. You can't really draw it correctly, but that's that red outline cylinder sits between the cylinder of radius R1 in the figure and the outer radius R2. And now we have to compute the flux through that cylinder. So first of all, we know that E, the electric field on that cylinder, is a constant value E in script and along the radial unit vector outward. The surface area is a surface patch, the soup can label patch, where you have an RD phi, so a little piece here, and you can see it better on this cross section. So there's my little RD phi, and then into the page would be the DZ. And if we in that direction, I can't really draw it in perspective, but if then you add up all these patches, you would just get the area of the Campbell soup can, of the area of the label, and it's also directed radially outward. So this is a feature of Gauss's law, that we always pick our surface on which the electric field is a constant and it's directed radially outward, in this case in the same direction as ds. That means any dot products we do are very simple, and the integral becomes a simple scalar value times the area of the Gaussian surface. So let's look at the details. All right, so here's our total flux is epsilon times the electric field right there. This is a constant. It's in the radial direction, and you can see we're dot producting a rho with a rho, and this is a straightforward integral to do, which we'll look at on the next slide. And on the right hand side we have the charge, which is sigma times R1 d phi. So there's an R1 d phi here, and then you can imagine into the page the dz. So we add all that up. This is a constant sigma, that's a constant, so we're just going to get a relationship of areas. So you can anticipate that this will look something like epsilon times E times an area, that would be the area of the Gaussian surface, is equal to sigma times the area of the inner cylinder surface. So we could call that IC, and that's Gaussian surface. So that's the relation. This is very similar to what you learned in Physics 253. Well, here is the algebra in a little more detail in Gauss's law. We have the integral for the total flux. There's no contribution except for flux coming out. There's no end cap contribution because E is only in the radial direction. So here we have these two, a rho dotted with a rho is 1. Epsilon, E, and rho are all constant, and so they come out of the integral, and then we have to integrate the phi, which just circulates all the way around. That gives us 2 pi. The z integral is the integral of a constant from 0 to L, so we get that. And this is just the area of our Gaussian surface. Call it AGS. On the right-hand side, charge contained inside that Gaussian cylinder is the double integral of the area of that inner cylinder, and that area is just going to be the charge density sigma multiplied by the area element R1 d phi. So R1 d phi would be a little arc like that, and dz into the page. These are constants. They come out, sigma R1. So there it is, sigma R1. The phi integral is the integral of a constant from 0 to 2 pi. It gives us 2 pi. The integral over z from 0 to L of 1 is just L, and that's equal to the charge Q on the inner cylinder of radius R1. And we solve for E, simple algebra, and we get this result here. The next step is we will use that to calculate the potential difference across the cylinder. All right, we're on the home stretch. We have computed this as the electric field. we're going to do a line integral in the potential, and we're going to go radially inwards in the radial direction. So our line element for the dot product for our force is equal to d rho times a rho. We substitute that into the potential integral. We're integrating from R2 to R1, and here we have our friend the minus sign. Now we substitute in, here's E right there. Here is the line element right here. We take the dot product of a rho with a rho, that's equal to 1. Now what's constant? Sigma is a constant, R1 is a constant, epsilon is a constant. They all factor out. And we have the integral minus the integral from rho equals R2 to R1 of what? Of d rho divided by rho, which is log rho. Evaluated the difference between the upper and lower limits. It's a log. We get this result here. And using the result that minus log of some ratio is just the log of the reciprocal, we get this final equation right here. And there it is. The next step in this calculation for capacitance is to compute the charge. Well, that's easy. It's the surface charge density times the area of that inner cylinder of radius capital R1, which is 2 pi R1 times the length, L, our soup can label. We substituted in for C. Here's Q. We just calculated it. Here's V. We just calculated that. And a bunch of things cancel out. And look what we get. We get an epsilon right there, which is the permittivity between the conducting surfaces. We get 2 pi. We have a length here, and this is a geometry factor. Everything works out. We always get something like epsilon times the G factor. I'll call it GF. Always, always, always. And the units of this geometry factor must be length. So they are. Here's L here, has units of length. The log is unitless. It's the log of a ratio, so everything is correct. And we also did that as a review in one of the classroom activities. Welcome to the third and final example. Exactly the same method as before. The integrals that we'll do are much easier. It's the spherical case. Again, we have an outer conducting spherical surface of radius R2, an inner conducting spherical surface with charge plus sigma, and this outer cylinder is grounded. General steps as before. Electric field first. Line integrated to compute the potential. Compute the charge and take the ratio. So here it is again. We have the charge on the positive inner sphere and the potential difference between the two spheres. And we never usually have to do an integral here. It's just uniform charge density times the area of that charged surface. In this case, the charged inner sphere of radius R1. All right, we use Gauss's law again, the electric field. What Gaussian surface do we pick? Well, we pick a sphere that's co-located, coaxial, concentric with the other two spheres. There I've drawn it, sketched it in red. It has a radius of little r. On this sphere, E is radially out and is a constant value. So we write it like this. Notice that the spherical element has whatever value it has. We won't write it out in detail. We'll just leave it like that. And the direction is in the same direction as the electric field. This is a property of all the Gaussian surfaces, is the direction of the electric field. And the direction of the surface elements are the same. So when we take the dot product of AR here with AR here, we'll get unity. Then E is a constant, and so the integral becomes very easy. The contained charge is also a simple integral, so let's put it all together. We use Gauss's law. It's epsilon E, which is D here, times times, meaning a dot product, the area element is equal to the charge contained inside. Here, GS refers to the Gaussian surface and IS refers to the inner sphere. So now we just do the integral in the next slide. So we know that E is constant on our Gaussian spherical circle. That's the dashed line here. And there it is, multiplying by epsilon, which is uniform. There's our surface element. Well, epsilon and E are both constant. Now we have the double integral of surface elements on the Gaussian surface, a surface whose radius is r. So what's the area of a sphere whose radius is r? It's 4 pi r squared. Now we do the same for the right-hand side. Sigma is a constant. It comes out of the integral. And now we're integrating over this inner spherical surface of radius r1. What's the area of a sphere of radius r1? What's the area of a sphere of radius r1? It's 4 pi r1 squared. Now we can solve simple algebra for the electric field constant, capital E. It's sigma r1 squared divided by epsilon little r squared. The 4 pi's have canceled out. So we get the final result. It's given right here. All right, what's the next step? We're familiar now with what to do. Calculate the potential. Do a simple line integral and then calculate the charge. Well, here we are, ready to do the final calculation. We just computed the electric field. Now we're going to do work, moving a unit test charge against the field, so radially inward. What is our line element? Well, it's dr multiplied by ar. Total work, dot product of E dot dl, minus sign against the field. Starting at the outer surface, little r equals r2. Going to the inner surface, little r equals capital R1. E dot dl, we just substitute that in. There's my E. There's my dl. The dot product of these two is 1. The constants come out. They are sigma, r1 squared, and epsilon. They go in front of the integral sign, and we have to integrate minus integral with the limits shown of dr over r squared. Well, that's 1 over r. Evaluated at the upper and lower limits and subtracted. Here's the result of doing this straightforward integration. Charge on the inner spherical surface is charge density times the area of the inner spherical surface, which is 4 pi capital R1 squared. Substitute in. There's the Q. And there's the V. And as always, the sigmas cancel out, and we get 4 pi epsilon R2 R1 divided by the difference. Does this work? Is it dimensionally right? Yes, we have length on the bottom, length squared on the top. So we have that general result of the permittivity times the geometry factor. I'll call it GF. And that has units of length. Now there's one more interesting feature of the capacitor that's spherical, and that is if R2 is infinite, this term here will be 0. This 1 over R2 will be 0. And this 1 over R2 will be 0. And so you can see from the algebra, as R2 is infinite, we can see that basically you're going to get what for the capacitance of an isolated sphere? C will be equal to 4 pi epsilon multiplied by R1. We could see that because if R2 is very large, we basically just cancel out the R2's here. You got infinity, infinity, so that's 1. You don't care about this, and you're left with this result. 4 pi epsilon r1 is the capacitance of an isolated sphere. Well, this brings us to the end of this application package on applications applying electric field calculations to computing the capacitance of 3 different geometries for parallel plate type capacitors, where we have 2 conducting surfaces separated by a dielectric. These applications were very good in reviewing, first of all, the use of Gauss's law in the classic geometries, then reviewing the application of computation of the line integral to calculate the potential, the work done against the field, and finally taking the ratios to compute the capacitance. We also did the straightforward example of the resistance of a rectangular box and got the classic result that the resistance is proportional to the length of the resistor divided by the conductivity and also divided by the cross-sectional area. This set of applications is a very good summary of all that we've done to date, but it doesn't include Coulomb's law and the boundary condition applications. To do this, we will do some more examples of capacitors in series and parallel and show how we use the boundary conditions to get the classical results of circuit analysis.